Okay, let's unpack this. We are in this incredible era of quantum computing where the hardware is just leaping forward. Superconducting circuits, ion traps, neutral atoms, you name it.
Yeah, they're getting bigger, more powerful, more complex. It's genuinely exciting stuff.
It really is. But there's a big, hairy problem lurking, isn't there? How do you actually write sophisticated programs for these complex machines?
Mm.
Not just theoretically, but programs that are, truly efficient and can run effectively on the specific, sometimes kind of tricky hardware you have access to.
Yeah, that gap between the rapidly advancing hardware and, well, the software tools available to program it effectively.
Yeah.
That's the core challenge right now.
Right.
We've really moved into an engineering phase for quantum computing, especially since maybe 2017 or so.
Yeah.
But the software evolution has been, well, maybe not quite as fast.
Totally. And the sources for this deep dive present what they call a radically different approach to tackling that exact problem.
Uh-huh.
It's inspired by a field that might surprise you. Electronic design automation, or EDA.
EDA.
Yeah.
Which is how complex classical chips are designed.
Exactly.
It's fascinating, really, to see how principles from something as mature as classical chip design might be adapted for the very different world of quantum circuits.
So our mission today is to understand this synthesis-based approach. We want to get to the heart of what it means, see how it actually works under the hood, look at the results it's achieving compared to what's currently available, and sort of figure out why the authors believe it's a necessary step towards truly scalable quantum software.
And it's all rooted in this paper, Design and Synthesis of Scalable Quantum Programs, plus some helpful supplementary material that gives us a look into their engine.
Great. So where do we start? Let's really underscore this software bottleneck they talk about first.
Right. As we mentioned, the hardware is moving incredibly fast. You have all these different modalities, superconducting qubits, trapped ions,
Neutral atoms.
silicon-based photonics. It's a diverse and growing landscape.
A real explosion of possibility.
Exactly. But the software side, well, the early platforms were designed mostly for specifying gates and, doing basic simulations or mapping a fixed circuit onto hardware using transpilation.
Which was fine when things were smaller and more experimental, I guess.
For sure.
Yeah.
But as algorithms and hardware got more complex, even later platforms that added higher-level concepts or libraries, well, they often built them on top of hard-coded, low-level implementations. It was like having a nice function call that represented something complex, but when you looked inside, it was always the same fixed sequence of basic gates, regardless of the context.
So you had abstraction in name, but not really in practice, like not true abstraction.
Precisely. The sources argue this lacked true abstraction. Current tools often map these higher-level constructs quite rigidly, and they tend to only think about resource constraints locally.
Locally, meaning within the scope of that specific function call, basically, not looking at the whole program. Okay, I think I'm getting it. The fundamental problem is that mapping a complex logical algorithm, like, I don't know, run this phase estimation subroutine or perform this matrix block encoding onto a concrete optimized gate sequence for a specific machine.
Yeah.
Doing that manually is becoming pretty much impossible for large, complex programs. And the existing compilation tools, they're built on taking a largely finished circuit and just adjusting it, right?
Right.
They aren't really designed for the scale and flexibility needed now.
You nailed it. It's not just difficult. For complex algorithms and larger qubit counts, it quickly becomes intractable to manage all the low-level details needed for optimization manually. It's just too much.
So if that's the wall we're hitting, what's this radically different approach they propose?
It's centered around this idea of true abstraction combined with synthesis.
Okay. And what does true abstraction mean in this context? What are we abstracting away?
It means allowing the user to express only the information that's essential to their problem.
Yeah.
That's things like the high-level functionality they need. Say, I need to add these 2 quantum registers plus any overall constraints they have.
Constraints like maximum qubits.
Yeah, exactly. Like, I can only use a maximum of 50 qubits, or the total depth needs to be under 1,000 gates. And maybe some optimization goals, like minimize the total number of CX gates.
And the key is what the user gets to leave out, right? All the fiddly bits.
Exactly. They omit all the messy details they don't care about, or maybe shouldn't have to care about.
Like what?
Well, how many auxiliary qubits does that addition actually need? How are those auxiliaries allocated and managed throughout the entire program? What's the best gate sequence for a multi-controlled X gate in this specific context, given the overall constraints.
Okay, yeah, stuff I definitely wouldn't want to figure out by hand.
Right. The user shouldn't have to specify any of that.
So who does figure all that out?
That's the job of the synthesis engine. It takes that high-level abstract description and fills in all details, not specified by the user.
Okay.
Its goal is to generate an executable quantum program that performs the desired function, meets the user's constraints, and is optimized according to their goals.
This sounds a lot like that EDA analogy you mentioned earlier, electronic design automation.
It does, yeah. In classical chip design, an engineer might describe a complex component, say a processor core, using a high-level language like Verilog or VHDL.
At the register transfer level, RTL.
Right, RTL. That description defines what the logic does functionally, but not the specific gates or wires. A synthesis tool then takes that RTL description and converts it into a lower-level netlist, specifying exactly which logic gates to use and how they connect, while optimizing for things like speed, power, or area, and making sure it fits the target silicon technology.
Right, you tell the classical synthesis tool what you want to do and the constraints, and it figures out the best way to build it from the basic components available.
Exactly. And because quantum computation often uses the circuit model, the sources argue this general concept of functional synthesis, moving from an abstract model to a concrete implementation, is directly applicable.
Okay. And they are careful to distinguish their definition of synthesis from, well, sometimes in quantum computing, synthesis just means decomposing one specific unitary matrix into gates, right?
Yeah, that's a much narrower definition.
But here, it's about generating the entire concrete program from an abstract description of its function.
Yes, exactly. It's not just about finding a circuit that works, but about finding feasible and ideally optimal implementations within the vast landscape of circuits that could potentially fulfill that high-level function.
Okay, so the core idea is this true abstraction that hides details the user doesn't care about or shouldn't need to. How does leaving out those details actually help with optimization and scalability? It feels a bit counterintuitive.
Well, by keeping the description abstract, you give the synthesis engine tremendous flexibility. It's not locked into one specific way of implementing something right from the start.
So because it's abstract, the engine has choices to make based on the global context, the whole program.
Exactly. Think about all the decisions the synthesis engine can make that weren't hard-coded by the user. There might be multiple types of implementations for a fundamental quantum operation, like an adder.
Oh, right, like different kinds of adders.
Yeah, you could use a quantum Fourier transform-based adder, or maybe a ripple carry adder.
And those have different resource trade-offs, right? Qubits versus gates.
Absolutely. One might need no auxiliary qubits, but be deeper in terms of gate count, maybe more CX gates, while the other needs auxiliaries, but is shallower, fewer gates.
So the engine can choose the best type of adder for the situation.
Right, and even within a chosen type, say ripple carry, there might be multiple ways to implement that at the gate level, different ways to arrange the controls and targets.
And it also decides things like how results are handled, where auxiliary qubits are used, even things like accuracy.
Yes. The engine decides if results are computed in place or require new registers. It manages the use of auxiliary qubits, which ones are needed, when they're needed, and critically, how they can be reused across different parts of the program. That reuse is key.
Okay.
The sources mention accuracy as something they can potentially manage too, distributing the required precision, although it's noted as still under development.
Wow. Okay. Managing auxiliary qubits alone sounds like a huge task the engine takes on.
It is, and it's not just within one function. Beyond single functions, the engine manages interactions between different parts of the program.
Like
Should two functions that need auxiliary qubits share the same physical qubits? When does a qubit need to be disentangled and reset so it can be used for something else? What's the best overall ordering of operations, especially if they share qubits?
Okay, these are precisely the kind of messy, interdependent decisions that are absolutely vital for optimizing a program for a specific hardware's constraints, things like total qubit count or circuit depth, but are completely separate from the mathematical function the algorithm is performing. Trying to keep track of all this manually for a complex algorithm would be, well, a complete nightmare.
It really would. You need a global view of the program's resource usage, which is something humans just aren't great at maintaining for large systems.
Yeah.
Now, the courses do acknowledge adapting EDA principles to quantum computing isn't trivial. There are unique quantum constraints.
Like the no cloning theorem.
Exactly. You can't just copy qubits like classical signals. There's no fan-out. You need to actively disentangle qubits to free up resources. Quantum states can have long-range correlations.
Oh.
Entanglement, right? And you can't just simulate small subcircuits locally to test them arbitrarily like you might in classical design.
But they show that they have successfully adapted these principles and are getting some pretty impressive results. Let's look at the examples they highlight. First up, the quantum walk on a circle.
Yeah, this is a nice pedagogical example, a good way to show the concept. Imagine a walker on a circle of two end nodes. You use qubits to represent the walker's position.
And qubits for the position.
Right. And another qubit as a coin that decides which way the walker moves left or right, say.
Okay, and the core operation is basically incrementing or decrementing the position register, which involves multi-controlled X gates or MCX gates.
Right, and this is where the synthesis comes in. The high-level model of the quantum walk just says, do a multi-controlled X. It doesn't specify how that MCX should be built from fundamental gates like CX and single qubit gates.
And as you mentioned before, there are multiple ways to build an MCX. Some need lots of O-qubits but are shallow circuit depth-wise. Others use fewer O-qubits but are deeper, more gates maybe.
Yes, exactly. The synthesis engine looks at the entire quantum walk program, considers the overall constraints you've given like maximum qubit width, and the optimization goals like minimize CX gates. And it dynamically chooses the best MCX implementation for each instance of the MCX operation within the walk. It's not one size fits all.
And the figures in the paper really bring this to life. Looking at figure 1 for the same quantum walk on 2R nodes. So 5 position qubits.
Yeah.
If you optimize for minimal width, like absolutely minimize the qubits used, figure 1b, you get a circuit using just 5 qubits. No auxiliaries needed, apparently, but quite a few CX gates.
Right.
But if you give the engine a bit more room, say up to 10 qubits total, and tell it to optimize for minimal CX count instead of figure 1c, you end up with a circuit that uses 7 qubits, so 2 auxiliaries, but significantly fewer CX gates. They do the exact same thing functionally, but the gate-level implementation is totally different because of the trade-offs the engine made.
And a big part of that optimization comes from the engine's ability to manage those auxiliary qubits globally, reusing them across different steps of the walk instead of them being tied to a single MCX instance.
Right. Trying to manually map, allocate, use, disentangle, and reuse auxiliary qubits throughout a large quantum walk circuit would be incredibly complex.
Oh, absolutely. Forget it for anything non-trivial.
And figure 2 drives this point home for larger circle sizes. Comparing their synthesis approach, using Classiq's engine, it seems, under different width constraints against results from other well-known tools like Qiskit, PennyLane, and TCAT, it shows a pretty dramatic difference, especially in the CX counts.
It really does. The synthesis approach yields significantly lower CX counts and scales much better in terms of gate usage as the problem size n grows. The gap widens.
And the sources attribute that scaling difference primarily to the way existing standard tools handle auxiliaries versus this synthesis approach. Is that the main factor?
That seems to be the core argument, yes. They explain that current tools often treat a function, like an MCX or an adder, and its specific implementation is kind of the same thing.
Yeah.
The auxiliary qubits needed for that specific implementation are essentially bundled with it. So if you use that function multiple times, the required auxiliary qubits just add up linearly across the program.
Oof, leading to very wide circuits very quickly.
Exactly. The synthesis engine, with its global view, avoids this by actively managing and reusing auxiliaries across the entire computation. It sees the bigger picture.
Okay, that makes sense. Let's move to the other example, the quantum singular value transform, or QSVT. This sounds like a much more complex, application-focused primitive than the quantum walk.
It is. QSVT is fundamental to a whole class of important quantum algorithms.
Okay.
Things like solving linear equations, simulating physical systems, loading data into quantum states.
Right.
It has potential applications everywhere, from finance to materials, science, plasma physics. It's a big one.
And the basic idea is embedding a matrix into a larger unitary operation, a block encoding.
That's the core technique, yeah. Block encoding the matrix you care about.
And their example involves block encoding a simple matrix A.
Correct. And the implementation of this block encoding relies on components like quantum adders and reflections.
Ah, adders again?
Yep. And crucially, just like the MCX gate, quantum adders have multiple implementations with different resource requirements.
You mentioned a QFT adder and a ripple carry adder before?
Those trade-offs.
Exactly. A QFT adder for an M-bit number might not need auxiliaries, but has roughly OM-at CX gates. A ripple carry adder might need M+1 auxiliaries, but only OM-CX gates. So a clear trade-off between qubit count and gate count.
And just like with the MCX and the quantum walk, the synthesis engine can choose which adder implementation to use based on the overall goals and constraints. It's not fixed.
Precisely. Figure 3 shows how, for the same block encoding function, optimizing for a narrower circuit, maybe because you have limited qubits, might force the engine to use the QFT adder, figure 3b, even if it means more gates.
While a wider constraint, more available qubits, allows it to use the more gate-efficient ripple carry adder, figure 3c, to get fewer gates by using those extra auxiliaries.
So you're giving it a budget, essentially, in terms of width or depth or gates, and it decides how best to spend it using the available building blocks.
That's a good way to put it, yeah. And figure 4 shows the results for applying the QSVT to generate a polynomial of matrix A for different matrix sizes.
Okay.
Again, the synthesis approach, using Classiq's tools, shows significantly better scaling in terms of CX gates compared to the other tools they tested against.
And for the same reasons we discussed, flexible implementation choices and smart auxiliary management globally.
That's the conclusion drawn, yes. The ability to choose the right adder type dynamically and manage the auxiliary qubits needed across the whole QSVT structure leads to much more optimized circuits, especially as the matrix size grows.
These examples make a strong case then. The ability to dynamically choose implementations and manage resources like auxiliary qubits based on a high-level description seems essential for tackling complex problems at scale.
They really do. It allows for optimizations that just aren't possible, or at least incredibly difficult, with rigid, hard-coded implementations or purely local compilation methods.
So how does the engine actually do this? What's going on under the hood to navigate this vast space of possibilities and find an optimal solution?
Yeah, the supplementary materials give some insight there. They explain that the engine essentially models the problem as a huge constrained optimization problem.
Okay.
It has to make all those unspecified decisions, which implementation for each function instance, how many auxiliaries, where they go, how to reuse them, the exact ordering of operations.
All those things the user didn't specify.
Exactly. And it has to do all that while satisfying all the constraints you set, like max width, max depth, whatever, and minimizing or maximizing a target metric like CX count or depth.
That sounds like a massive search space. How does it even begin?
It is massive. They use a propagation-based constraint satisfaction problem, or CSP solver, to tackle it.
A CSP solver.
Yeah, you could think of a CSP solver as trying to find values for a set of variables that satisfy a set of constraints. Here, the variables represent all those implementation choices and resource allocations throughout the quantum program.
Okay, so it finds a solution that fits the constraints. But how does it find the optimal solution, not just any solution?
Good question. They use a technique called branch and bound on top of the CSP solver.
Branch and bound.
Yeah. It finds an initial valid solution that meets the constraints. Then it adds a new constraint that says, basically, find a solution that's even better according to the optimization goal, like fewer CX gates than the last solution.
Ah, okay.
And it repeats this process, systematically exploring the possibilities until it can prove that no better solution exists within the constraints.
But how does it avoid just trying every single possibility? That sounds like it would take forever, even with pruning.
Well, that's where the propagation and pruning mechanisms of the CSP solver are really crucial. The solver propagates the implications of each decision and constraint across the entire problem.
What does that mean, propagates?
It means if you make a choice here, say use a ripple carry adder, which needs 5 OQB, that constraint propagates. Those 5 qubits are now marked as in use for that part of the circuit, which restricts choices later on.
Got it.
And using techniques like ERC consistency, you can often determine early on that certain combinations of decisions are impossible or guaranteed to be suboptimal given the constraints and other choices already made.
So it eliminates bad branches of the search tree early.
Exactly. This allows it to prune away large parts of the search space very efficiently without having to explore them explicitly.
Ah, so it's not blind searching, it's smartly eliminating bad options as it goes based on the global picture.
Precisely. And this global perspective, where decisions in one part of the program immediately affect the possibilities and constraints in other parts, is key. It's fundamentally different from traditional multipass compilation.
Right.
Which typically performs local optimization step by step and might miss these crucial global interactions, like how auxiliary qubits could be cleverly reused across different logical blocks if you planned it right from the start.
This really feels like a necessary evolution of quantum software tools, then. Why does this EDA-inspired synthesis approach matter so much for the future, according to the authors?
As they state, they see it as a robust, scalable, and long-lasting way to develop quantum software, essentially the way forward.
Because it lifts the burden of low-level circuit design from the user, lets them think at a higher level.
Exactly. It enables that true abstraction we talked about. Instead of the user specifying how to implement a function down to the individual gates, they specify what the function is and their overall resource goals and constraints. The dynamic synthesis engine then makes the crucial context-dependent decisions about implementations and resource management decisions that transpilers, which operate on fixed low-level circuits, simply cannot make. They don't have the flexibility.
And this flexibility isn't limited to just minimizing CX gates or circuit width, presumably.
No, absolutely not. Once you have this kind of synthesis framework, you can potentially optimize for other critical factors.
Like fitting the hardware better.
Yeah, like minimizing the number of swap gates needed to fit a specific hardware topology, especially if it isn't fully connected. Or maybe optimizing for other hardware-specific constraints or noise characteristics.
It really sounds like it moves the focus from being a circuit-level artisan painstakingly wiring things up to being able to think about the problem you're trying to solve at a higher, more functional level.
That's the goal, to make quantum programming more accessible and scalable by providing tools that can handle the immense underlying hardware complexity automatically, or at least semi-automatically.
Of course, they also acknowledge that this is still a developing field. It's not like all the problems are solved. What are some of the remaining challenges they point out?
Well, a significant one they mention is the full management of the accuracy resource.
Accuracy resource.
Yeah. This means figuring out how to distribute the required overall accuracy of a large, complex algorithm across its various building blocks. Different parts might tolerate different levels of approximation.
Oh, okay.
And this gets even trickier when you factor in hardware noise, which is crucial for near-term NISQ devices. How does the inherent noise affect the accuracy you can achieve, and how do you make trade-offs?
That sounds incredibly tricky, balancing the mathematical accuracy you need with the messy reality of noisy qubits and imperfect gates.
It is. And looking even further ahead into the fault-tolerant era, they point to the very challenging problem of co-designing and co-synthesizing the logical quantum program and the error correction code it will run on.
Wow. Okay, so the program itself and the way it's protected from errors have to be designed together, optimized together.
Exactly. Those two things, the logical algorithm and the physical implementation with error correction, operate at very different levels of abstraction. Figuring out how to optimize across both simultaneously is a major open problem.
That sounds like a whole other level of complexity.
It is. They mentioned they've worked on related areas like optimizing logical qubit placement for fault tolerance, but full co-synthesis across these layers is presented as a big future hurdle, a grand challenge, really.
So, recapping this deep dive, we've looked at this paper proposing an EDA-inspired synthesis paradigm for quantum software. It seems pretty compelling.
Yeah.
We've seen how moving to true abstraction allows an engine to dynamically make complex implementation decisions and manage resources, like those crucial auxiliary qubits, globally.
Taking that burden off the programmer.
And we've seen some pretty convincing results on examples like the quantum walk and QSVT, showing significant potential improvements over methods lacking this global optimization capability.
Yeah, the scaling benefits looked quite substantial in those examples.
And we got a little peek under the hood at how the engine uses a CSP solver with smart pruning to navigate the huge design space and find optimized solutions from that high-level description.
Turning that abstract description into concrete, efficient gates.
It really feels like this kind of approach is going to be essential for the future, allowing quantum software to keep pace with the hardware and, move beyond manual circuit-level crafting for complex tasks.
It seems like a necessary step, yeah.
Yeah.
It's just the complexity where it belongs into the automated tools rather than burdening the programmer with all those low-level optimization details.
So a final thought for you, our listener, to ponder. Given the increasing power of quantum hardware that we're seeing, how quickly will software synthesis tools like this become indispensable for achieving real-world quantum advantage? And maybe more interestingly, what new possibilities might they unlock once the focus really shifts from building the circuits gate by gate to simply defining the problem and its desired outcome at a higher level?